We solved this problem in the last class using Barn-Haber cycle, and we made a Barn-Haber cycle. Then we used the formula of Barn-Haber cycle. What is that formula? That is delta HF. Delta HF is equal to sublimation, latent heat of sublimation plus ionization energy of metal plus half dissociation for monovalent anions from divalent molecule, and there we have used negative electron affinity, so that is creating some kind of trouble. So let's use plus EA plus lattice energy. So the negative term, and this is also negative term actually, those negative signs are taken care by the numbers, because electron affinity we express in negative numbers, lattice energy also we express in negative numbers, and those we substitute here, they become negative. So this is the best way to memorize the equation. So that's the Barn-Haber cycle and Barn-Haber cycle equation. Without using this formula also, just with the observation of these equations and clever manipulation of these equations, we will arrive at the answer. So what are we going to do here? We need to find out electron affinity of chlorine atom. That means this is the final equation we require. So let's take this one as a path 1, and we use remaining all reactions in such a way that we arrive at this equation. So that is path 2. Therefore X in path 1 is equal to the sum of all those manipulations we do in path 2 using these thermochemical equations will be established, and from that the X value, which is essentially electron affinity of chlorine, will be determined. Okay, now when we solve problems with the application of Hess law, we must take care of the final equation we require. Based on the final equation requirement, we select the individual thermochemical data equations and we use them, sometimes directly, sometimes we reverse. When we reverse the thermochemical equation, delta H value for that reverse reaction will also change from positive to negative or negative to positive. And another thing, if any reaction required with a different coefficients than in these data equations, then that equation must be multiplied with a suitable integer to get suitable thermochemical equation required for manipulation. At the same time, enthalpy data also must be multiplied with the same number. So let's take this equation, which is our final requirement, which requires chlorine gas as reactant, chlorine atoms as reactants, electrons as reactant, and chloride anion as product. So when we select the data equation, we must select something that has chlorine atoms, gaseous chlorine atoms as reactants. So that is clearly this equation. This equation has chlorine gas but 2 moles, but in the final equation we require 1 mole of chlorine atom. Therefore this reaction must be divided with 2, so that makes half Cl2 and that gives Cl gas. But the data equation has the chlorine atoms in gas state as products, but in the final equation we require chlorine atoms as reactants. Therefore what we need to do, we need to reverse this reaction. Two things are happening. We must divide this reaction with 2, same time heat number also will be divided by 2, and also we are reversing. Therefore what I do here, I reverse this equation, then divide with 2. When I reverse, the heat of enthalpy of the reaction will take minus sign. So here I write the Cl gas to half Cl2 gas, and delta H enthalpy change for this reaction is half of the data equation with negative sign. That's going to be, how much is that? Negative 245.2. So negative is coming because of the reverse, and division of 2 coming because we require only 1 mole chlorine atoms. So that gives negative 122.6. Negative 122.6 kilojoules per mole we use finally. So at least we are able to get this the chlorine gas, which are atoms, as reactants. Our next job is we need to get Cl minus as product, and also this chlorine gas must disappear in the final equation. Therefore, next thermochemical equation should be taken in such a way that this half Cl2 must cancel out. So we shall use this equation that has half Cl2 as reactant. The first thermochemical equation has Cl2, half Cl2 as product. Now the second equation we are using has half Cl2 as reactant. So that is formation equation. So we get Na plus Cl minus solid. This is delta H formation, and its data is, we must use the same because we are not reversing the reaction. Therefore, no need to change the sign of the enthalpy of reaction, and at the same time no need to multiply with any integer because we are taking the equation as it is. Okay, the final equation should not contain this solid. Therefore, next equation we take must be able to cancel out this one. Therefore, let's use the reverse of what is that called, the lattice energy. And also one more thing here coming on the reactant side, sodium solid, which also should not be there in the final equations. So therefore the next data equation must be the one that should cancel the sodium solid or sodium chloride solid. Let's take this cancellation of the sodium solid. For this we use the sublimation reaction, which is in a reverse way, because there Na solid to Na gas is there, but here we need sodium solid as product. Therefore the data equation must be reversed. So Na gas to Na solid, and for that the data equation is reversed. Therefore enthalpy also changes sign to negative, and all these energies are expressed in kilojoules per mole. So let's write it. The next one is cancelling the sodium solid is over. Now we must cancel the sodium gas. To cancel the sodium gas, we take the next equation with sodium gas as product. So that is actually ionization potential reaction in a reverse manner. So ionization potential is endothermic, opposite is exothermic. So this enthalpy of this reaction is a reverse of ionization potential, that is negative 493.7 kilojoules per mole. And finally, what are the things we have cancelled so far? This is cancelled, this is cancelled, this is cancelled, and one more thing has to be cancelled out. What is that? Sodium chloride solid must cancel out, and sodium solid must cancel out. And for that purpose we select the remaining thermochemical equation, that is lattice formation equation, in reverse manner, which is lattice breaking. So therefore for that I write equation Na plus Cl minus solid, lattice breaking, to Na plus gas, Cl minus gas, and it is reverse of the data equation. So that means that's going to be positive 791.2 kilojoules per mole. Okay, that gives us sodium ions cancelled, NaCl, NaCl cancelled out. So therefore, if we add all these reactions, what is the final equation we are getting? Cl gas, reactant, electrons as reactant to produce Cl minus gas. So the actual reaction of Cl gas plus electron to Cl minus gas, which is electron gain enthalpy reaction, this is a direct reaction. This is a series of reactions. Enthalpy change associated in this process or sum of enthalpy changes in all these processes is same. Therefore, the enthalpy change for this change is sum of all these enthalpies. Therefore, delta H of process, the delta H of the process, that is electron gain enthalpy of chlorine atom, is sum of all these numbers. What we get here, let's see. The same thing, 791.2 minus 122.6 minus 411.3 minus 109.6 minus 493.7. So that's going to be negative 346 kilojoules per mole. The same answer we got. And what's the difference here? We have not used Barney-Haber cycle and the formula. Just with the help of data equations, with suitable manipulations, we will be able to arrive at the electron gain enthalpy of chlorine atoms. So, Hess law is very useful in finding enthalpy changes for many reactions, for which determination of enthalpy change may be difficult, or sometimes the reactions are so slow there is no point in waiting for such a long time to determine their enthalpy values. If we have another route that can give us the result very quickly, that quick application, so that gives enthalpy changes for a particular combination of reactants to products, can be calculated from Hess law. Therefore, Hess law is very, very helpful. Let's go to the next problem, where let's take this problem. What is the problem here? Two forms of carbon or graphite, soft, black, slippery material used in lead pencils and as a lubricant for locks. And the second form is diamond, a brilliant hard gemstone using enthalpies of combustion for graphite, which is negative 394 kilojoules per mole, diamond negative 396 kilojoules per mole. Calculate delta H for the conversion of graphite to diamond. So this is our final equation, required equations. And enthalpy change for this process can be calculated from the combination of these two reactions in a suitable way. So what we do here, we take one of these reactions first, then we take the second reaction appropriately, maybe direct or reversing it, so that we will be able to arrive at this equation, and the summation of heats of those individual processes will give us the enthalpy change for this transformation. So the final equation has carbon graphite as reactants. That means the data equation that contains carbon graphite must be with carbon graphite as reactant. That is data equation 1, that has graphite as reactant, which is same as our final reaction, graphite as reactant. Therefore, no need to change the first data equation. So let's take the first data equation as it is. What is that? Carbon graphite solid plus oxygen gas to carbon dioxide gas. Enthalpy is same. We are not reversing the reaction and we are not multiplying any number. So therefore this is negative 394 kilojoules. The second equation we must use in reverse. Why? Carbon dioxide must cancel out, oxygen must cancel out, and diamond should appear as product. To make that happen, the second equation must be reversed. So that gives us carbon dioxide gas to carbon diamond plus oxygen gas. And what is the delta H for this? This is going to be positive 396. Why? We have reversed the data equation. The data equation has a negative 396 kilojoules and we have used in reverse manner, and for that the enthalpy change is the sign. So negative 396 becomes positive 396 for the reverse reaction. And now we should add these two reactions. That gives the carbon dioxide cancels out, oxygen goes away. Now we have carbon graphite to carbon diamond, and for this process enthalpy change is simply positive 2 kilojoules. So carbon graphite to carbon diamond, the enthalpy change is only 2 kilojoules. From graphite to diamond. Yes, the enthalpy change is only 2 kilojoules. It looks that very little energies are coming out, or very little energies are required, very little heat is required to convert graphite into diamond. That's not the case. This is the enthalpy change, that is enthalpy of products minus enthalpy of reactants. What's the main factor here? When graphite in the process of becoming diamond, it should pass a critical state that is called activation state or transition state, and for that process it requires a tremendous amount of activation energy or a path that is very difficult to achieve. That's why the attempt of converting the graphite into diamonds are so far not successful. The reason is it has a kinetic problem. So that's the problem with this. Now let's go to the, before we go to the next problem, it's another point coming from this problem. Thermodynamics clearly tells about the energy process, energy released or energy required in the overall process in a chemical reaction or a process, but it doesn't tell about whether that process happens or not under a set of conditions. That's the restriction of the thermodynamics. That domain is chemical kinetics, where a particular reaction proceeds slowly, relatively good speed, or very fast. That's a separate domain, that is chemical kinetics. We don't handle that now. Now we are going to next problem. Okay, the problem is diboron is a highly reactive boron hydride that was once considered as a possible rocket fuel for the US space program. Calculate delta H for the synthesis of diboron from its elements according to the equations. This is formation equation of diboron. So this is the final equation we require. To get the enthalpy change for this reaction, we don't need to perform this reaction, and this reaction may not be possible because of the kinetic issues. Though this reaction possible or may not be possible, we will be able to find out enthalpy change for this process with the help of Hess law. Now, the final equation requires boron solid as reactant. The first data equation has boron solid as reactant. Okay, we use first data equation as it is. Any requirement of multiplying with any number? Let's see. The coefficient of 2 in the final boron in the final equation is 2. The data equation is also 2. Therefore, no need to multiply with any number. No need to divide with any number. Let's take the first equation as it is without any multiplication or division. So that gives us first step of the path 2, B2O3 solid, and delta H for the process is negative 1273 kilojoules. Now let's go to the second step, where we need to cancel out B2O3 solid. For that purpose, we shall select the second equation and we reverse it. The first equation is giving B2O3 solid as product. To cancel that, the second equation must be taken with B2O3 as reactant with the same coefficients. Therefore, no need to multiply any number or divide with any number. So that gives us second equation reversed. B2H6 gas. Now B2H6 gas. Now product is taken care with the second data equation plus 3 oxygen gas. Delta H, as we have reversed the data equation, we must change the sign from negative to positive. That gives positive 2035 kilojoules. And another thing we should see is the things that are remaining. So this is cancelled out. Oxygen is 3 by 2 O2 on the reactant side, 3 O2 on the product side. That means still we have 3 by 2 O2 oxygen on the product side and 3 moles of water gas or gaseous water on the reactant side. They must go, and also the H2 gas 3 moles should come on the reactant side. So for that purpose, let's take data equation 3 that has H2 gas as reactant, but we require in the final equation H2 gas 3 moles. What should we do now? Data equation 3 must be multiplied with 3. So that gives us 3H2 gas, 3 by 2 O2 gas. Why? 1 by 2 is multiplied with 3, that gives 3 by 2 O2 gas to 3H2O liquid. We have not reversed the reaction, therefore no change in the sign of the enthalpy. But what is the change happening here? As the reaction is multiplied with 3, enthalpy also must be multiplied with 3. That makes 286 times 3. 3 moles of oxygen, hydrogen to with same reaction requires 858 kilojoules. Sorry, 858 kilojoules of heat is released because it is combustion of hydrogen. The final one, it is 3 by 2 O2, 3 by 2 O2, 3 by 2 O2, that is 3 O2 and this 3 O2. They cancel out. And what else are remaining? H2O gas on reactant side, H2O liquid on product side. Those two must cancel. To cancel that, we should take the data equation 4. Should we reverse it or should we use it directly? Let's verify. H2O gas, so far when we add these 3, we have it as reactant. To cancel this, data equation must be taken as H2O gas product, and the data equation is directly having H2O gas as product. Therefore, we use this one as it is, H2O liquid to H2O gas, and no need to change the sign of the enthalpy, and no need to multiply or divide with any number, because we are not doing any multiplication with the equation, not doing any division with the equation, not reversing the reaction. Therefore, enthalpy remains as it is, that is 44 kilojoules. What happens now? H2O liquid. Oh, sorry, we missed here. Now look at here. H2O, we have H2O gas, we have 3 moles, but the data equation has H2O gas and H2O liquids are 1 mole. That means they must be multiplied with 3. When they are multiplied with 3, this heat data also must be multiplied with 3. That gives 132 kilojoules. Now we shall cancel 3H2O liquid, 3H2O liquid, 3H2O gas, 3H2O gas. Now what are we getting? We have 2 boron gas on reactant side, and other one is 3H2 gas. So reactant taken care. Now on the product side, we have only B2H6. So finally we have arrived at the required equation. So that is 2 boron solid plus 3H2 gas to B2H6 gas. And for this purpose, or for this reaction, enthalpy change is sum of enthalpy changes associated in all these processes. So this is a direct path. It's a series of paths leading to the same product from the same set of reactants. So therefore, what is the enthalpy of formation of B2H6 is 132 minus 858 plus 2035 minus 1273. That's going to be 36 kilojoules. Delta H for this reaction is going to be 36 kilojoules. That's how we solve the problems using Hess law. So in the next class, we shall also do some problems on Hess law and also calorimetry. What is calorimetry? Measurements of heats of reactions is known as calorimetry, will be covered in the next class. Calorimetry and 1 or 2 problems on Hess law again. Thank you very much.